Right, in this video I'm going to look at transducers. They are divided into two. We do have input transducers and output transducers. Input transducers are usually connected in a potential divider circuit. Now be sure to watch the video on the potential divider circuit first before you watch this one, because you will understand the potential divider or the use of the input transducers more if you have a knowledge of these potential divider circuits. In output transducers, you find that they tell you whether a signal has been processed or not. So examples would be LEDs, loudspeakers, microphones. Microphones could work as either input or output. We do also have buzzers and lamps. So all those are output transducers. Now we're going to start off by looking at the input transducers, and the first example is the thermistor. Now a thermistor is a device whose resistance varies with temperature. So we're going to consider the negative temperature coefficient thermistor first, or in this video we're only going to look at that. So we said that a thermistor is a temperature dependent resistor. So a negative temperature coefficient one would mean that its resistance falls as the temperature increases. So in this diagram here, where you have resistors, the thermistor T and the resistor R, so this will be a known resistor, or yes, a known resistance of a resistor. And then we do have this thermistor. So the symbol for a thermistor is like that. So it's a resistor with a line drawn like that. So please do remember this one, we memorize it. Now, as we have gone through the potential divider formula, we said that the output voltage will be equal to this resistor, or the resistance, divided by the total resistance T plus R times 6 volts in this case. So which means if this thermistor is in the cold, it has very, very high resistance, so it gets the lion's share of the supply voltage. In other words, there will be more resistance there, hence more potential difference there, and less output potential. So the output potential difference would approach 0. Now when it is in the hot, then the resistance falls. So when the resistance falls, it means its PD also falls, and the PD across R would increase. So you've got more output PD flowing through there. So an application of this could be a temperature warning device that tells you that the water maybe has reached its boiling point, or the water in the geyser is hot enough. So if it's hot, then it sends a signal to the alarm to tell you that the water is hot. So when the temperature of the thermistor increases, this resistance falls, so the PD across T falls. Correspondingly, the output PD across R increases. The increased output voltage can be used to switch on a relay. We'll talk about a relay very soon, allowing current to flow to the bell, which rings as shown below. So that's a temperature warning device, or an alarm to indicate higher temperature. So the circuit for that alarm is as shown. So you have a bell. So the bell is connected there to then we've got a relay, and then a relay is a magnetic switch. So what it does is it receives the small signal that's coming from there, and then it operates, because the bell may be using a larger current. So which means the relay just switches on the circuit which has this bell, and then we have the bell sounding. Now the next input transducer is the light dependent resistor. Now the LDR, that's the short form for light dependent resistor, it does have a high resistance when it is in the dark, and a very low resistance when it is in the light. So high resistance in the dark, we're talking of about 10 mega ohms, that's 10 to the power of 6 ohms, and much lower resistance was about 1 kilo ohm, 1000 ohms when it is in the light. So they can be used in electronic circuits to switch lights on and off automatically and in photographic meters. Right, so if you look at this diagram here, we do have an LDR that has been connected in series with a known value of resistance R. Now, when this LDR is in the dark, like I said, it has a very high resistance. So it's high resistance, which means the PD across it will be high. So it gets a greater share of the 6 volts, and with nothing coming out from the PD, from the output PD. And then when it is in the light, then its resistance falls, and thereby having more voltage on the output than up there. So the increased output voltage can be used to operate a relay and switch on a bell as in the previous circuit. Open again, so that if the light falling on the LDR is removed, the PD across the resistor and the relay drops so that the relay contacts open again. Power to the bell is cut and it stops ringing. So LDRs, like I said, they can be used also to show the level of darkness, or maybe in street lights when it's dark and then you want the street lights to operate on their own. So when it is dark, we have got nothing there, which means that these street lights or these lights will tend to go off when it is in the dark and then go on when it is in the light. Now, if you want a reverse of the situation, if you want the lights to switch on when it is dark and then off when it is light, then you need to put the LDR down there and then the resistor up there, so that output PD is going straight from the PD, from the LDR. In both sensor circuits, a variable resistor may be used in place of the resistor R. Yes, so which means you could change the resistance and then determine output PD for a certain temperature or light or brightness. So if you want a specific value of the resistance, that would give you that when the LDR starts to light up or starts to go off, you could use a variable resistor there. Now, I've been talking about the relay, and we need to shed more light on it. So the relay consists of an electromagnet. So this is a wire that is wound on a core, iron core, remember. So the iron core concentrates the magnetic field to itself, thereby creating a stronger magnet. So if you have DC, you have got to use DC here, so that you have got one value of the magnetic field that is created there. So when the first switch is closed, then you're going to have magnetic field created in this iron core, and then this becomes an electromagnet. So an electromagnet, remember, is the magnet whose magnetism is only there when there is a current flowing. When there's no current, then there's no magnetism, and then nothing happens. So in this case, I said if we close the switch, then there's magnetism, and this attracts this iron armature. Because this is made of iron, it will be attracted there. When it does that, by pivot action, it pushes the contacts to close. And then when these contacts close, we do have a second circuit, which is a generator, a motor, or something that uses a larger current. So with a relay, a small current in one circuit can be used to switch on another circuit which uses a large current, as I've explained. So that's the symbol for a relay, switch symbol for a relay. This represents the electromagnet, and this represents the switch that then closes. Okay, so the appliance is there. Then you've got the main switch. As long as there's no current here from the 0 to 5 volts, then this appliance will not work. But when you close this switch, then there's magnetism there that closes this contact and makes this a complete circuit, and the appliance works. The relay also isolates the low voltage circuit from the high voltage mains supply. Right, so I think I'm going to end the video here. Then in the third video, I'll talk about diodes and rectification. I'll talk about diodes and rectification. So signing out.